The last report of this session is Kisaka. Luminosity of synchrotron radiation in pulsar magnetospheres.
I'd like to talk about synchrotron radiation in pulsar magnetosphere. I'm Shota Kisaka from Ayamogakuni University. I focus on X-ray and optical emission. This is a this is a luminosity plot. Gamma ray, X-ray, and optical as a function of spin down luminosity. X-ray and optical are considered as considered as a emission from particle created by a high energy photons. So, in fact, efficiency of synchrotron, efficiency of optical and X-ray radiation is lower than gamma ray. So X-ray and optical emission and the combination of gamma ray emission provide useful information to understand the pair scale process in the magnetosphere. So now the detected number sample size become large. So we check the conventional model, the synchrotron radiation model, using a simple analytical model. In our model, accelerated particle in magnetosphere emits curvature radiation, and curvature radiation created a pair with non-zero pitch angle. This particle emits synchrotron radiation. We consider two pair creation process, magnetic pair creation and photon-photon collision. We consider separately. We make some assumptions that all physical quantities are described by a function of radius from the center of the star for simplicity. And we only consider the rotation part pulsar. So the maximum luminosity is limited by the spin down luminosity. For the magnetic field structure, we consider dipole field dominant at near the right cylinder. For inner part, we also consider the non-dipole effect. And in the photon-photon collision case, we see the photon as thermal X-ray from heated polar cap. Of course, for young pulsar, thermal emission from entire surface also contribute to the seed photon, but we mainly focus on middle age and old pulsars. Age is about older than 10 to 5 years. So we neglect the thermal emission from entire surface. Model parameter is only one. In dipole case, we explain later. This is the luminosity of synchrotron radiation described by here. P is the power of synchrotron radiation for a particle, and N dot is the total number flux of synchrotron emitting particle. This is a time scale advection and cooling. First is a primary particle. Total number flux of primary particle is described by here. We introduce a model parameter ether, energy conversion efficiency, the ratio between the total energy flux of primary particle to spin down luminosity. And for the Lorentz factor of primary particle, in photon-photon collision case, photon-photon collision mainly occur at outer magnetospheres. As a region, high energy gamma ray photon most of high energy gamma ray photon can escape free from the magnetosphere. So we use the typically observed gamma ray energy to estimate the Lorentz factor. For magnetic pair creation case, we use a full potential drop across the polar cap. But in this case, the result doesn't depend on the Lorentz factor. We will explain later. Second is curvature photons. Number of curvature photons for a particle is described by the power of curvature radiation, time scale, and the characteristic energy of curvature photons. Next is the pair creation efficiency. We separately consider the two-photon collision and magnetic pair creation. This is a two-photon collision case. Optical depth is approximately described here. We consider the thermal emission from heated polar cap as a seed photon. For the luminosity of temperature, we use typical observed value. And this is the collision angle between X-ray and gamma ray. In magnetic pair creation case, because pair creation is very efficient, so we consider the most optimistic case. All photons with energy higher than the maximum escapable photon energy at a given region convert to pair. So we consider the higher generation pair as a synchrotron emitting particle. In this case, the total number flux of synchrotron emitting particle is described by here. In this model, the total number flux is determined by the total radiation energy, and the maximum escapable photon energy. So, either model parameter ether and this energy determine the total number flux. Don't depend on the Lorentz factor of initial primary particle and the typical energy of curvature radiation. Last is the synchrotron power. In this model, we fix the observed frequency and calculate the Lorentz factor of synchrotron emitting particle. Using this Lorentz factor, we calculate the synchrotron power. Okay, other quantities which depend on the magnetic field structure is our pitch angle, curvature radius, and magnetic field strength. In photon-photon collision case, emission region is mainly outer magnetosphere. So we only consider the dipole case in this scenario. Then pitch angle, curvature radiation, and the magnetic field is here, zeta equal 1. But magnetic pair creation case, emission region is mainly inner region. So we also consider the non-dipole effect. We introduce additional parameters, alpha 0 and zeta. We mainly use alpha 0 equal unity, and the result doesn't depend on zeta b so much. In our synchrotron model, there are some constraints on emission region. First is the energy condition. Particular energy determined by the high energy photon have to be larger than the energy of synchrotron emitting particle determined by the observed frequency. Second is the variety of synchrotron radiation here. And last is the pair creation threshold, like this. This is the result of our model. in X-ray case, X-ray luminosity, observed X-ray luminosity here, and we plot the maximum luminosity for a given spin down luminosity and magnetic dipole magnetic field. In photon-photon collision case, emission, maximum luminosity is done. Light cylinder at the light cylinder luminosity become maximum. And magnetic percolation case, emission region is near the star surface. Green and magenta is gamma ray pulsars. Most of young gamma ray pulsar non-thermal luminosity is lower than the model limit. We fix the parameter eta equal 1. So this line corresponds to the upper limit of the luminosity in our model. But low spin down luminosity pulsar, photon-photon collision model doesn't. Luminosity in photon-photon collision model is lower than the observed value. So maybe another emission component are required for these pulsars. And for very low luminosity pulsar, to explain the observed luminosity, non-dipole effects are required. Next is flux ratio between gamma ray and X-ray. In our models, gamma ray luminosity is described by here. Luminosity is proportional to the model parameter eta and spin down luminosity. And X-ray also is proportional to the model parameter, so flux ratio does depend on model parameter. So our model predicts this line. The width corresponds to the range of magnetic field. But for most pulsars, flux ratio is below the model prediction. And for young pulsars, we neglect the thermal emission from entire surface. This could increase the X-ray flux because percolation efficiency increase. So this is not a maybe not a problem, but for low spin down luminosity pulsar, maybe another mechanism or another emission location are required to explain these flux ratio. This is a result for optical. Results are very similar to X-ray, but we emphasize that for 0108, if this luminosity comes from this this pulsar and this is non-thermal, emission is not a synchrotron radiation because the random level at the magnetic percolation region is much higher than 1 eV. So it doesn't expect to emit the synchrotron radiation in that region. This is a flux ratio for optical. Result is very similar to X-ray. Okay. So for low flux ratio or ratio of the gamma ray pulsar with low spin down luminosity, we discussed some possibility to solve the model discrepancy. So our possibility is the multiple accelerator model. If gamma ray come from outer region and X-ray also come from inner region, then observed luminosity could be explained. In this case, maybe light curve in gamma ray and X-ray is very definite. This is other possibilities like here. In some, this is a summary. Thank you for your attention.
Can you please return 3 slides back?
Sorry.
Can you please return 3 slides back?
Please slide.
Yeah, yes, this one. So, first of all, I have a small remark. Basically, you have a whole range of possibilities between dipolar field and many different non-dipole field. So, what you call non-dipole field is actually one of the smallest scale magnetic field which you can find on a neutron star. So, it's kind of theoretical upper limit. And I have a question. What caused this change of stiffness around logarithm of luminosity 32?
Yeah.
Why that pulsar is so much different? Or you cannot explain it?
Here?
Yeah.
Because in non-dipole case, non-dipole in our model, non-dipole effect is only here, here, here. Not determine the scale or the particular magnetic field structure. In that model, we use alpha equal unity. This value gives a maximal luminosity, and but this line determines this line determines the condition of validity of synchrotron radiation and percolation threshold. So if magnetic field become large, percolation threshold, the lower upper bound of the percolation region become large, but the synchrotron, validity of synchrotron condition also become large. So, these conditions determine this line.
Yes, I too am going to probe on the non-dipole. The pair yield is very sensitive to the field line morphology at high altitudes. And so field line sweepback, as in the Deutsch solution, is very important to include. Is that what you've treated in your non-dipole in order to get the enhanced synchrotron luminosity?
Yeah. Yes. Yes, we use very static dipole. Yes.
So you've just introduced a parameter to describe the enhanced pair opacity and pair yield, as opposed to modeling it directly with the field line structure at high altitudes. Is that correct?
Opacity, optical depth is here. No.
Okay, let's talk about it at coffee. Okay, thank you.
So we have no time for any questions. Now we have coffee break. Thank